let's run through an example, and we'll have more next lecture, but this is the generator of the Poisson process. So let X be a Poisson process of rate mu. The question is, what is its generator? The transition probability for the Poisson process is Poisson, and we know it takes the following form. So now what we have to do to get the generator is take a derivative and set that derivative set time to be 0 in that derivative. So we can do this case by case, kind of a case by case basis here. One thing we clearly know right away is that the generator for xy is 0 when y is less than x, and this is because the transition probability is 0. The Poisson process always goes up, it never transitions downwards, so that transition probability is 0. Taking the derivative of 0 gives you 0, so this is the simple case. Next case, which is a little bit more complicated, is y is equal to x, in which case the transition probability is non-zero. In fact, if you plug in y equals x in this formula, you'll get e to the minus mu t, and this is all we're taking a derivative of right here. Minus mu t pops down, and here I've just replaced the e minus mu t by the original probability. What we do know is that the probability of moving from x to x in time 0 is equal to 1. This is true not just for the Poisson process, for any continuous Markov chain, this is going to be the case. And so in that case, all that remains is writing down the final answer for this particular case, which is r, the generator at xx, is equal to minus mu. Now, let's look at the case y greater than x. This is the last remaining case that we have. This is maybe the most complicated of all three cases. And let's see, so I've just written up here what the transition probability is. And what I'm going to have to do is apply the product rule. So I'm going to have to take two derivatives. The first one, I'm going to consider the derivative with respect to this last term here, e to the minus mu t. So e to the minus mu comes downstairs, and the rest stays intact. The next derivative I have to take is for this part of the product, which is mu t raised to the y minus x power. So you see the y minus x coming down. That's good. And then by the chain rule, derivative of mu t gives you the mu out front. And then in the final step, I'm cleaning things up a little bit. The y minus x leads to a cancellation with a y minus x minus 1 factorial on the bottom there. So now, time to plug in t equals 0. And again, you have to be a little bit careful. Setting y is equal to x plus 1, you'll notice the following thing happens. This term right here will be linear in t, so setting t equals 0 gives you a 0. In this case, that doesn't quite happen. The mu t raised to the 1 minus x minus 1 is actually 1, because 1 minus x minus 1 is 0. So what you have is the only dependence on t is really up in the exponent here. So that gives you a 1. And the denominator there is just 0 factorial, which is 1 again, leading to this value of the generator. So rx to x plus 1 is equal to mu. And you'll notice that if we had insisted that y is greater than x plus 1, both of the terms in here, so this entire expression will be dependent on t in kind of a polynomial way. So plugging in t equals 0 gives you 0 for the generator. Now we can combine all this from with the results that we had earlier. We had rxx is equal to minus mu, and we also had rxy is equal to 0 for all y less than x, and this gives you a full description of the generator. It seems that there are only two values that are non-zero: rxx, which is minus mu, that's this one right here, and rx to x plus 1, which is equal to mu. Clearly, at least from recall, mu was involved in the description of the rate of the underlying continuous time Markov chain. And so what we're about to see in the next clip is that the generator is going to be related to the rates of the CMTC. And so this example kind of motivates that, and we're going to dig into the details in the more general case next.